This is Calculus Section 2. I'm going to be finding the volume by a method called the disk method. So this whole front side of the notes is nothing but information, so we're just going to run through it together real quick, and then we'll take a look at some examples on the back. All right, so it says if a rectangle were rotated about an axis of revolution, it would create a solid in the shape of a disk or a cylinder. To find the volume, you'd have to take the radius of the disk, r, and square it and multiply it by pi. Then you would take that area of the circle and multiply it by the width of the disk, W. So what this is saying here is if I had this rectangle and I were to take it around this line and start rotating it around, what would happen is it would create this solid disk that you see over here. In order to find the volume of something that looks like this is basically like a really short cylinder. And to find the volume of a cylinder, you find the area of the circle, and then you multiply it by the height of the cylinder. So the area of the circle is just pi r squared. So that's our pi and then our big R squared. The height here, instead of calling it a height, they're calling it a width, so times W. So that's how we're finding the volume of the disk. Here it says if there were many disks of varying radii, we could find the volume of the irregular shape by shape created by rotating a curve around the axis of revolution by finding the volume of each disk and adding them up. So what they're saying here is if instead of just a straight line where I have rectangles here, what if it was some kind of curved line? So what you would do is we would come in and start adding different rectangles in here. Each of these rectangles then would have a radius of this distance here, which is going to change as we move along our curve. Our width then of each rectangle, they're calling this delta x. And as we do all of these rectangles around together, we create all these different disks, which is going to give us an approximation of the volume whenever we add all of those individual disk volumes together. So then, kind of like we did whenever we were talking about area under a curve, when we first started our integration, our limits and our summation things, we said that if we were to take them, and here it says increase the number of disks to infinity, then we would find the actual volume created by the curve. So just like whenever we were doing our rectangles underneath a curve to find the area, and we increased the number of them until it was an infinite number, which fit underneath the curve exactly, now we're doing the same sort of thing, but with volume. So here they have the limit as delta goes to 0 of pi, the summation from I equals 1 to n of r of x sub 1 quantity squared delta x. What this is doing, this here, this r of x sub 1 squared, this is your radius squared, times pi, and since pi is a constant, you're able to take it outside the summation. This delta x is going to be the width of these rectangles, so it's how that's changing there. Here the summation from I equals 1 to n. N means here we're going to have however many rectangles to create these different disks that we would have. So here there's 1, 2, 3, 4, 5, 6 disks. So if we wanted to find it just like this, we would just go to 6. And then here our limit as delta goes to 0, this is different than what we've seen before in that whenever we did these things before with area, it was the limit as n went to infinity. But what they're doing here, this delta is going to be this change in your width, and they're saying when that width goes down to basically 0, then it becomes those straight lines, which is going to find the exact volume in there. So it's just a different way of denoting it. But it's the same sort of thing that we were doing before, where you're just finding an infinite number of them. And then we learned that taking the limit of a summation is the same as doing an integral. So this is going to be the formula that we're actually going to use to find the volume of the solid that's created when we take a curve and we rotate it around an axis of revolution. So you're going to have your pi, the integral from a to b, so however far apart, so here a to b, so that distance between r of x quantity squared, which is basically just then our function squared, dx. All right, so if we flip on over then to the back side, here it shows depending on which way we're rotating as to which variable it is we're going to be in respect to. So if we're talking about a horizontal revolution axis, so like here going around the x-axis, in order to create a disk, the rectangle would have to sit upright and rotate around this way, just like we saw in that last example, which means then our radius of the disk is going to be measured from the bottom up. When we measure up, it's in terms of x's, so it would look just like we had on the front, and our delta x is our dx. If we're doing a vertical axis of revolution, so like going around the y-axis, in order to create a disk, our rectangle would have to go out to the side, and whenever you measure out to the side and not top to bottom, out to the side is going to be an x equals equation, or it's going to be something in terms of y. So we're going to end up with a dy, our change in y, our limits of integration is going to carry along the y. So depending on whether it is horizontal or vertical is going to tell us whether or not we need to be in terms of x or in terms of y. All right, so this first problem here, they tell us that they want to find the volume of the solid by revolving f of x equals the square root of sine about the x-axis from 0 to pi. So here they've already got the picture for us. They have the arrow drawn here to show that we're going about the x-axis, which means in order to create disks, we're going to have a vertical rectangle here standing up so that it comes around and creates a disk this way. Here's a picture to show what it would look like here at the end after we've rotated the entire thing and made the solid. So now as we're doing this, if we are going to plug into the formula pi times the integral from a to b, because we're measuring up, we need to be in terms of x. So it's going to be r of x quantity squared dx, because this is like pi r squared times the height, to find kind of like the volume of a cylinder. So on here, we're going to have that pi. Our limits of integration, we're going from 0 to pi. And now our radius is going to be the height of this rectangle, which is just from the x-axis up to the function, and the function is the square root of x. So that means we're going to take the square root of, sorry, not the square root of x, the square root of sine of x. We're going to take that and square it dx. Now, before you actually integrate any of this stuff, you always want to go in and square your r and then do your integration. So it's going to be pi from 0 to pi. The square root of sine quantity squared, the square root and the square cancel out, and you just get a sine x dx. Now, when we go to actually integrate it, we've got the pi in front. The integral of sine is a negative cosine, because the derivative of cosine is a negative sign, and since it's a positive, we need a negative so that we have a double negative to get the positive. So we're going from 0 to pi. So now it's going to be a matter of plugging in our upper and lower limits to evaluate and end up getting our final solution. So we still have the pi in front. We need to take the upper limit minus the lower limit. So upper limit is pi minus the lower limit, which would be minus a negative cosine of 0. And then here, just a reminder, whenever we're talking about cosine of pi and cosine of 0, 0 is straight to the right on your unit circle, which is the point 1, 0. Pi is straight to the left, which is the point negative 1, 0. Cosine is the x value, so we're looking at 1 and negative 1. So cosine of a pi is a negative 1. This negative is the negative that was in front of the cosine. Then we have a minus, and then another negative, and now cosine of 0 is 1. So lots of ones, lots of negatives. We got to be careful here. If I go through and take my double negatives and turn them into plus signs, a minus and negative is going to be a positive, another minus and negative is going to be a positive. I end up with 2 here times the pi in front, tells us that the volume of that curve when it's rotated around the x-axis is going to make 2 pi. All right, and flip over now to the next page to example 2. Example 2, we're going to find the volume formed by revolving f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. So for this one here, our function here is the 2 minus x squared. This here is the g of x equals 1, and what that does is it bounds just this top part of the parabola that we're going to be rotating. And we're rotating at about that line y equals 1, so it's just right here. So we are measuring rectangles going up, so we're still in terms of x like we were on the last problem. So when we set this up, it's still going to be pi times the integral from a to b of r of x, quantity squared dx. So we have our pi. This one, our limits that we're integrating through, it starts here at -1 and it goes over to 1. So we're going from -1 to 1. And now our radius. We want to know basically the height of this rectangle here. And it's going to kind of be like what we did in the first section whenever we were finding the area between two curves. We always had to take the upper curve minus the lower curve in order to figure out what that distance between them there was going to be. So over here, if I kind of work off to the side, I have to take the upper minus the lower. My upper curve is 2 minus x squared, and my lower curve is just that line y equals 1. And if I combine here, the 2 minus the 1 is going to make a 1, and then the minus x squared. So that's going to be my r of x that I'm going to plug in and end up squaring. So 1 minus x squared, quantity squared dx. And now again, before you do any integration, you always want to square. So this is going to become a pi times the integral from -1 to 1. And here, don't forget, that's a binomial being squared. So whenever you do it, you would actually have to write it out twice and do all of your distributing. So it would be a 1 times 1, which is 1. I'd have a 1 times a negative x squared, and then another 1 times a negative x squared to make a -2x squared. And then a negative x squared times another negative x squared is going to be a positive x to the 4th. And then dx. And now we can go through and integrate. So the pi is still in front. Here when I integrate the 1, I just get an x. Here when I raise the power and divide by the power, I still have the -2. Raise it to a cube divided by that 3. And then here with the x to the 4th, raise the power to a 5 and then divide by that power 5. And we're evaluating from -1 to 1. So now I just need to go in, plug in all the 1s, and then plug all the -1s in and simplify. So I still have that pi in front. First, if I plug in the 1, that's going to give me a 1. Here, that shouldn't have been a minus and negative. Let me go back and fix that. I apologize. I shouldn't have put the negative in twice. So here, that's going to end up being a 1 cubed, which is 1. 1 times 2 is 2. Over 3 is 2/3, and it's a minus, so minus 2/3. Here, if I plug in a 1, 1 to the 5th is 1. Over 5 is just 1/5. And now minus my lower limit. It's supposed to be a minus in there. Got my parenthesis a little close. Here, when I plug in a -1, I just get a -1. Here, when I plug in -1 into x cubed, I'm going to get a -1. Times the 2 is a -2 over 3 is a -2/3. But there's this minus here, which is going to make it a plus 2/3. And then here, when I plug in a -1 into an x to the 5th, I'm going to get a -1 and then over 5, so minus 1/5. And now if we get our calculator and plug all of this in, all of that stuff in here is going to end up being 16/15. And when you multiply it by the pi, it just becomes 16 pi over 15. So that's going to be how we do that disk method. Now, the thing is here, it says sometimes when a curve is revolved around an axis of revolution, it creates a solid that contains a hole. When this happens, we're supposed to use a method called the washer method. So just like if you think like with tools and stuff, a washer is the thing that basically kind of looks like a donut. It's round, but it has that hole in the middle. Whenever you take something and you rotate it, and whenever you rotate it, it creates that hole in the middle. So like this piece here, if I took it around, it's going to create this shape here, but it's actually open all the way through. because it has like part of it cut out, that's going to be your washer. And the way that you find stuff like that is if I were to find the volume I would get if I took the whole thing and rotated it around, so this thing becomes solid, and then I actually took the inside piece out and subtracted it, that would then take away the whole and give me the volume for what's left. So here's the formula representing that. This big R of x, that's that outside radius. So here, this outside distance here. Then you subtract this little r of x squared, which is going to give us then that radius on the inside. If I were to distribute that pi, this is a pi r squared, that would become a pi r squared. So you're taking then and finding the volume created by the outside, the volume created by the inside, and just subtracting them. So last examples then on the back. Example 3 says to find the volume formed by revolving the region bounded by y equals the square root of x and y equals x squared about the x-axis. So you can see here, if I took this y equals the square root of x and this y equals x squared, and I rotated it around the x-axis, it's going to create a shape that actually has this piece cut out on the inside. So because there's that inside piece cut out, I'm going to have to do this with the washer method. So it's going to be pi times the integral from a to b. It's going to be the big R of x, quantity squared, minus the little r of x, quantity squared, dx. So as then now for my big R of x and my little r of x, I go from a to b. First off, my big R of x is going to be that outside radius, which on this one, the one on the outside, is this curve here, which is my y equals the square root of x. So square root of x, quantity squared, minus, and now my inside radius is this line here, which is your y equals x squared. So minus x squared, quantity squared, and then dx. So again, on this one, before we do any kind of integrating, we want to square these terms here. So this is going to be pi times the integral. Oh, but I didn't mean to continue to put a and b. We are integrating from x equals 0 to x equals 1. So from 0 to 1. If I square the square root of x, I'm just going to get an x. And here, if I square an x squared, I'm going to get an x to the 4th. So minus x to the 4th dx. Now we can actually go through and integrate. So we're going to have a pi. If I raise the power and divide by the power, that becomes an x squared over 2. Here, if I raise the power and divide by that power, it becomes an x to the 5th over 5. We're evaluating from 0 to 1. So now I want to go through and actually plug in the 1 minus when I plug in the 0. When I plug in a 1 squared over 2, I get a half. When I plug in a 1 to the 5th over 5, I get a 1/5. If I were to subtract the lower limit of 0, the thing is I'm just going to get a 0. So we could write it, or you could leave it just like this. And then if I take 1/2 minus 1/5, I'm going to get 3/10. Put it with the pi makes a 3 pi over 10. And then the last problem, example 4. Example 4 tells us to find the volume formed by revolving the region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So this is the first one that we've done that hasn't been around the x-axis, it's been around the y. So if we're going around the y-axis, in order to create a disk, we're going to have to measure out from left to right to find our height. So everything now is going to be in terms of y. So now we're looking at that pi from, and I'm going to call it like they did in the formula, c to d. And then we're going to end up having our r of y, quantity squared dy. But we're going to have to be careful because even this is going to be a little tricky, simply because if you look here coming along the y-axis, I have two different pieces here with different radius, meaning from 0 to 1, you can see this is one big solid chunk. So these rectangles are going to be constant the whole way through. But then as soon as I get from 1 and go from 1 to 2, now the size of these rectangles are going to end up changing. So what we're actually going to do for this is we're going to divide this and think of it almost as two separate problems where we're going to find two different volumes, and then we're going to end up adding them together. So if I start with just this bottom one here, my r of x is this distance out, and this distance out is just a 1. So for this first part here, I'm going to have a pi. Here we're going from just 0 to 1 on the y. My r is just a 1, so it's a 1 squared and then dy. Now, as for the second one here, this one I'm going to be going from 1 to 2. So I'm going to go ahead, I'm going to have to add them together. So I got my plus, there's my pi, integral from 1 to 2. But now for this one, in order to find how tall each of these rectangles are going to sit, I'm going to end up doing just like we did whenever we were finding the area between two curves, just like what we did on example 3 above. It's going to end up creating this piece with a hole in the middle. And you can kind of see in the 3D picture, there's this bowl part that's been cut out. Because we're cutting out, that's going to end up being a washer method. So we're going to need our big R minus our little r. And you can see here they've already got labeled. My big R here is the same as the big R we had down here. We can just label that's just going to be a 1. And you know what, here, I apologize. I put r sub x. That really should have been an r sub y because we are working in y's. All right, and then now my little radius is this distance here. Now the only catch is and why I caught myself here is we're supposed to be in terms of y, which means it's supposed to be an x equals equation. But if you come back to the beginning here, they didn't give us an x equals equation. So what we're going to have to do first is solve this thing for x so that then we have an x equation that we're able to use. So if I were to solve for x, I would have to subtract the 1. So I'd have y minus 1. And then to get rid of the square, you have to square root the whole thing. And you can look here, they actually have that written here, that little r equals the square root of y minus 1. So that's our little r here. So we are going to end up having to take our big R squared, which our big R is 1, minus our little r squared, which the little r here is that square root of y minus 1, and then squared, and then dy. Now, again, before we do any kind of integration, we want to go through and simplify our squares. So this first one becomes pi, integral from 0 to 1. 1 squared is just 1 dy. Plus pi, the integral from 1 to 2. Here, a 1 squared is 1. Minus, and here, the square root of y minus 1 quantity squared, the square and the square root will cancel. And we're just going to get a y minus 1. But do keep in mind, it's minus that whole thing. And then dy. And then one last thing before I actually integrate, and this first one I'm just rewriting. I can combine like terms here. First off, that 1 would distribute, so that's really a plus 1, and 1 plus 1 is going to make a 2. So this is pi, the integral from 1 to 2 of 2, and then minus y dy. And now we can go through and integrate both of these. So for the first one here, I have my pi. The integral of 1 is just y, and I'm going from 0 to 1. Then I have my pi. This next one, the integral of 2 is going to be a 2y. Here, negative y, I have to raise the power and divide by the power, so minus y squared over 2. And this one's going from 1 to 2. And now I'm going to go in and plug in my upper and lower limits to evaluate it and get my final solution. So here, if I plug in my 1, I'm going to have pi. This would be like a 1 minus 0, which will just be the 1. And then here, I have my pi. If I plug in the 2, 2 times 2 is 4. Here, if I plug in the 2, 2 squared is 4 over 2, which is 2, minus evaluated at the lower limit. So if I plug in a 1, 2 times 1 is 2, minus, and here if I plug in a 1, 1 squared over 2 is a half. Here, if I go through and combine all of these numbers, I'm going to end up with a 1/2. Here, a 1 minus 0 is just a 1. So really, this is like saying a pi plus a pi over 2, which is going to give us a 3 pi over 2. So when you're doing your disc and washer method, it's basically the same. It's just the idea with the washer is you're cutting something out. So you're going to have a big R squared and a little r squared. But it's all going to follow this basic formula of pi integral from a to b or c to d of your radius squared and then dy or dx depending on the variable you're working in. So homework for this, not too many problems, just 5 of them. After you get a chance to work through them, if you have any questions, let me know.